Hello and welcome to this CDP Studio demonstration. CDP Studio is an integrated development environment geared towards developing, commissioning and maintaining hardware-independent real-time dynamic control systems. There are actually two products: the CDP Framework, a set of libraries enabling real-time and hardware-independent distributed computing, and CDP Studio, an IDE that simplifies the use of the CDP framework. There are three workflows or roles in CDP Studio. The developer has all the features enabled and creates the function blocks in C++ for the projects. This is typically a software developer. The project engineer assembles the control systems without programming, using the CDP standard functions and the custom-made function blocks. This is typically a system engineer or automation engineer. The service engineer commissions and tests systems and support end customers. This demonstration will show how to create a system by assembling and configuring pre-made function blocks, how to create your own function blocks with new functionality, both from pre-made blocks and by writing them in C++, and how to create a user interface. I will finish off with information on supported industrial protocols and how external tools like Excel can be used to create and configure CDP systems. I start by creating a system, then I select the framework version. There will be more about versions later. A system contains one or more applications. The application type can be console or GUI. Console applications are real-time control applications with only text-based output, while GUI applications include a graphical user interface to visualize data from and to command the control applications. CDP Studio comes with a wide range of pre-made functions. These are typically mathematical functions used in automation systems, various industrial protocols, and pre-configured setups for well-known industrial hardware vendors. The available resources depend on what is currently selected. To get more information about a specific resource, select it and click F1 to go to the help page for that resource. I will now demonstrate how to create a project using pre-made functionality simply by dragging in pre-made objects and connecting them together. I drag in a sine generator and then an absolute value operator. By connecting the sine output to the ABS input, values will automatically propagate from the sine output into the absolute value operator. When I do run and connect, the application is run on its configured target, which by default is the development computer. The value goes from the sine into the absolute value operator, where the generated output value is always positive. I will now show you how to create new functionality by making a more complex reusable function block from pre-made functions. I am here adding an empty component that I will call add100 that will serve as a container for other objects. I then add an input signal and an output signal to it. This is now part of its external interface. I drag in an add operator into this component and connect the input and the output. The connection information is stored in the configuration for the add100 function block. I then set up the add operator so that it adds 100 to the input. When we check the configuration for the output signal, we can see that the routing property has been updated. The output is set to retrieve its value from .add.out, which is shorthand for demosystem.add100.add.out. I can run and connect to show how this works. Initially, the input is 0 and the output is 100. I can change the values during runtime to do simple tests. If I change the input to 1, the output changes to 101. The function block I made is a self-contained, easily reusable block with a well-defined external interface. It reads its inputs, executes the logic, and writes the output. Let's test the function in a system before making it a reusable block. The sine has an output signal as part of its API, that generates a sine wave between -1 and 1. I can route the output from the sine into the add100 component that I made. Routing a value connects the data source to the target and updates the configuration in the target to reflect this. I could of course use any of the other available resources as a data source, for instance MQTT, CanOpen or OPC UA, but I have chosen a sine for its simplicity. When you choose Run and Connect, the application binary is compiled, linked and deployed. CDP Studio then runs it and connects to the live application to display real-time data from the application. By default, the application will run locally using the local loopback interface to not disturb the network. The connection in the IDE is made over an API that also has Python, Java and JavaScript client implementations available to accommodate interfacing from third-party applications. You see that when I run this, the add100 output varies between 99 and 101. The add100 works as intended, so let's now make it reusable for other projects. Reusable objects are stored in libraries. When you create a library, you select which framework version to use from the available versions. Many of our customers operate in industries where there are strict regulations on testing related to new software versions. CDP Studio has been made with this in mind, so once a framework version has been released, only carefully vetted bug fixes are applied to that version. CDP Studio supports a range of different hardware platforms, and the libraries must be built for the hardware where it will be used. Simply tick the required toolkit boxes. A toolkit is everything needed to create an executable for the target device. Different toolkits and new CDP versions can be added and removed from the Package Manager, accessible from the CDP Studio Help menu. The Package Manager lets you install, remove and update toolkits on a per framework basis. Note that this update is always safe to do. It does not upgrade your project. It only improves the development IDE and may provide critical bug fixes to the toolkits. Okay, back to the library. I can take the component I made, which is essentially just a configuration, and I can store it in the library as a reusable block. Just select the configuration you want to make reusable, copy it, and then paste it to the library. There you can change its name, and even modify its configuration further. I will now show you how you can create new functionality by creating function blocks and programming in C++. CDP Studio comes with a set of wizards that automatically create the framework and code structure. The CDP component is the most typical code block. It can have a state machine, and the current state's processing function will run at a set frequency in Hertz in real time. The CDP node model should be used when very lightweight code blocks are needed. It's typically used to expose the simplest classes to the CDP Studio configuration tools. CDP operators are blocks with a single real-time process function that can be added to the configuration. Operators manipulate values in transit or on the fly. Operators can have 0 to many inputs and 0 to many outputs. CDP port is used to interface objects. The threaded component model should be used when a code block is needed that can do blocking I/O in a separate thread. Frequency is how often a component runs, and priority is how important it is that it runs when the system is overloaded. These are initial values that can be changed later. The wizards generate the required boilerplate code to get started faster, and to allow the user to concentrate on the functional part of the given block. The aim of CDP is to allow users to utilize the full power of C++ while avoiding the typical problems that arise when writing complex large-scale software. CDP function blocks remove control dependencies, data dependencies, and time dependencies in code, making the resulting function blocks smaller, self-contained, and with a well-defined API. The goal is to aid in and enforce reusability of these blocks. This is the auto-generated header file, and this is the auto-generated C++ file. The desired real-time code should be put into the process null function. This is the default null states processing function. It gets called periodically at the configured frequency. Since the process function is a slice of real time, blocking or time-consuming computations should not be performed here. Instead, the threaded component model should be used. That creates a separate main function where such workloads can be performed. The API of the code block is made up from smaller objects that can be added to provide ways to receive and send data to other code blocks, and to allow configuration of the block's behavior later during the system assembly phase. The provided code generator can make many different interface variables to cater for varied needs of data communication between blocks and for varied ways to do configuration. Signals are similar to wires between blocks. They are real-time values that are propagated automatically to other subscribing blocks and provide one-to-many periodic data connections. Properties and parameters are persistent values to allow altering the block's behavior later when it's used in a system. Alarms generate events that can, for example, be displayed in an operator panel UI. Events provide many-to-many eventful data connection. Message handlers can be added to the component to handle incoming messages, and a connector specifies a link to another object that can be used to send messages and read state and status information. The message connector pair typically provides a many-to-one eventful data connection. I will now add a few signal objects to make up the code blocks API. During system assembly later, I will show how the blocks can be connected into a data flow to perform the wanted functions. Different primitive data types can be selected in the type selector. The initial value can be set and description can be added for API documentation purposes. It's also possible to use the Graphical editor to add objects. You can also do bulk editing. As can be seen, the code generator adds the variables to the header file, and it automatically adds the boilerplate code that ties the variables to its configuration. It also adds and updates the model file, which declares the class API. The model file is used as a description of the code block for the tools after the library is built. We write the code inside the state process method. In this case, there is only the null state, and we want out to be the sum of in1 and in2. Note that you can get context-sensitive help by pressing F1. The generated signal variables can be used to write the desired functionality, and inside the code block, they don't care where the data comes from or where the output data is used. This provides an efficient way to decouple data and control flows from the actual code block. Building a library produces and exposes resources for later use when assembling the system. It is only when the library is built that it is copied and exposed to the resources. When you build a library, it's built for all the toolkits you specify in the Deployments tab. Additional toolkits can be downloaded via the Package Manager. The block that was made is now available as a resource that can now be used as part of the system. One or more instances of the block can be added by dragging, double-clicking, or using the context menu. We now have a reusable component, and it can be used in exactly the same way as the add 100 component that I made earlier using just drag and drop. The connection behaves like a wire. Every time the simple adder component runs, as defined by its fs property, it reads the value on the wire, then runs the process function to compute the out value, and then the out value is updated. We can now run and connect to verify that our component works as intended. The values in the in1 input are now received from the sine component. As you can see, the output correctly varies between 99 and 101. The Analyze mode allows you to plot any value in the system and is very useful when testing and tuning systems. Here we are plotting the sine output, and as the default cycle time was left at 5 Hz, steps in the signal are clearly visible. I can add items that I use often to the watch window. This gives me quick access to items both in configure mode and in analyze mode. The watch window now gives me easy access to the sine frequency signal. The cycle time is now 10 Hz and the prominent steps in the signal are less, as the sine is executed and produces an output 10 times a second. By setting the frequency high enough, the stepping is reduced. You can of course debug applications as you do in a normal IDE. You can set breakpoints, inspect variables, step into and over functions, and do everything that you're used to do in the debugger. When you're satisfied that your application is working correctly, you might want to run it on something else than your local PC. In configure mode, select the Deploy Configuration tab. From there, you can select the network to deploy to. Once a network is selected, the network is scanned for suitable targets. Simply name the devices you want to use and pair them. From the Applications table, you can select which target and toolkit the application should use. CDP Studio will warn you if you need to build some libraries for the target toolkit. Add the toolkit to the library deploy configuration, then deploy the library. From now on, when you select Run and Connect, the application will run on the selected target using the selected toolkit. Since CDP Studio provides an API that abstracts you from the hardware and operating system, there is no need to rewrite any code when you choose a new target. I will now demonstrate how to connect a user interface to the control system. In the user interface design mode, the connections are always made from the UI side, both for getting values and for setting values. This is in contrast to configure mode, where connections are like subscribing to values. This approach gives the benefit that the control part of the system does not need to directly know about the UIs. It also makes it easy to have several UIs against the same control system. There is a large set of widgets that CDP Studio provides that uses the same tag or name-based routing to get or set data values. Widgets contain different routing properties to access values in the system for different purposes. I am setting the demo system app.sine.output as a data source for the widget. Since the sine value is between -1 and 1, it will not fit well in the current meter that ranges between 0 and 100. There are several ways to solve this. The sine output can be changed to have a different amplitude, or a scaling operator can be added to the output signal. You can of course also change the range of the meter to be between -1 and 1, and it's also possible to set local scaling in the widget itself. I want the widget to show the sine as a value between -100 and 100. The filter on top of the properties table can be used to filter for wanted properties. Since the sine varies between -1 and 1, I choose to make the widget scale the value. It is possible to press F1 to get help on the different properties. As we can see from the help, CDP scaling is multiplied with the incoming value. The meter will now show the value of the sine multiplied by 100. As with the pre-made function blocks, the user interface is completely driven from the configuration and doesn't involve any coding. When the system is run, both applications in the system start, and the UI application automatically connects to the control application. In fact, we have now created a real-time distributed system, as the user interface runs on my local PC, while the control application runs on the Raspberry Pi. We can see that the sine generates a value between -1 and 1. The meter receives the value and does local scaling on it before displaying. The user interface is mostly SVG based, and there is support for themes. It also has a night mode and a day mode, which can be toggled during runtime. It is possible to make your own themes by editing SVG files in either Adobe Illustrator or by using Inkscape. This gives you the possibility to create widgets with a unique look. It is also possible to embed a web view or to use QML to create a more animation-friendly user interface. This completes the user interface part, and I'm now going to show you how to control something in the physical world. This is usually done by talking to a device that can convert between data bits and physical signals such as voltage, current, pressure, and so on. The talk is typically handled by a protocol, and in CDP, this is handled by an I/O server. I/O servers are implemented in libraries in the same way as I showed earlier, except most I/O servers derive from the threaded component. As you can see, we provide a range of ready-made I/O servers that implement various protocols, such as I2C, CANopen, Modbus, MQTT, NMEA, OPC UA, etc. We also have a powerful I/O server called External Control I/O. This can run local files, do HTTP, FTP, SCP, REST, SMTP, and other interesting stuff. Users can implement their own protocols, and we continuously update CDP Studio with the relevant protocols for various industries. Some of these protocols are highly configurable and require some knowledge and skill to configure. We provide examples and tutorials for each protocol to get the user started. As an example, you might be familiar with GPS, the Global Positioning System. The NMEA 01A3 I/O is an I/O server that can read GPS data. It can also send GPS data, so you can use it to simulate a GPS device. It can be easily added to an application by dragging it in and configuring it. You typically configure the transport, so it knows how to communicate with the GPS device, and then you configure which data to transmit. You must specify where to read or write the data. In this case, it is which COM port the GPS receiver is connected to. In addition, you must set up the baud rate, etc. of the device. This can be found in the datasheet for the device in question. To further simplify the setup, some I/O servers have pre-made configurations that can be added and modified as needed. We have here provided a typical data block received from a GPS device. Latitude and longitude, along with north-south and east-west signals, can be used to determine your position. Since NMEA is not restricted only to GPS, it is also possible to set up your own NMEA sentence. For instance, to exchange data with some third-party application. You just have to specify a unique header and add your signals. To get values into and out of the I/O servers, value routing is used just as you would in a normal component. As I showed in the beginning, once you have configured something that you want to reuse, you can just copy it and paste it into your library. When the library has been built, it is available as a resource you can later use to populate your system. To complete this demonstration, I will now show how CDP Studio can integrate with external tools to create control systems. This can be anything from importing I/O and tag information from physical design tools, using configuration scripts to assemble systems, or just simple copy and paste to Excel, as we will now demonstrate. I will now create a new function block in LibreOffice by simply copying a component, modifying it, and pasting it back. I change the name and add a new signal called distance. You can now see the new function block is added to the system. As CDP Studio is under constant development, new features are being added all the time to improve the product and to simplify developing real-time applications. To see other interesting features about CDP Studio, take a look at our CDP Studio YouTube channel. I hope you found this demo interesting. If so, you can download a free trial of CDP Studio from cdpstudio.com.